Welcome all of you. We have been discussing about scalar coupling, and especially last one class and two classes we have discussed extensively about the multiplicity pattern, because that is very important, especially when you are working with a complex molecule. The pattern what we are going to get is very important if you know what is a pattern, so that you know how to extract the coupling information. See, if your aim is just to characterize the compound and say, okay, I have got a CH3 peak, I have a CH2 peak, just for a assignment purpose without getting into the pattern coupling information, just for identifying whether the molecule what you have synthesized has particular peaks to characterize it, that is a different question. But if you want to get the coupling information etc., to get more information about the structure of the molecule, geometry of the molecule or conformation of the molecule, then these patterns are very important to understand. Only then you should know how to interpret the spectrum. And for that we took several examples and understood about the multiplicity pattern. One proton coupled, hypothetical molecules I took, one proton coupled to another single proton or CH2 proton, CH3 proton, and then when it is coupled to two groups of protons, single or multiple like chemically equivalent groups like CH2 or CH3. And I showed that when one proton is coupled to CH and CH2, it is going to be doublet of quadret or doublet of triplet, depending upon which coupling is larger. If the CH2 coupled to CH proton is larger, it will become triplet, then other one will be a doublet. So, it will be doublet of triplet or triplet of doublet, depending upon which coupling strength is larger. Exactly the pattern gets reversed. Okay. Similarly, you can have CH2, one proton coupled to CH2, CH3, or another 2 CH2, 2 CH3s, or one varieties of combinations we can think of. And I showed for many examples I took. I showed you the example with a stick plot, how we get the multiplicity pattern. But always remember, when you have a multiplicity pattern for any particular group of protons or a particular proton, the center of the multiplicity corresponds to your chemical shift. If it is a triplet, it is the center of the triplet line. If it is a quartet, center of the quartet line. If it is a doublet, center of the doublet, like that. And then further multiplicity gives rise to splitting, further splitting because of various coupling. But how do you measure the coupling also I explained to you, which coupling is larger, which coupling is smaller. See, this needs some sort of expertise. You can start working with that for a couple of examples. If you do it, you will know by looking at the pattern how do you get the coupling. Okay, with this today we will do some take some examples and do exercise ourselves to understand and identify the splitting pattern. What I showed you was a stick plot. What is the real complicated spectrum we get in the realistic example? How do you get that? We will go ahead and do that. For example, this is the spectrum which we have got. What do we call that pattern? 2 lines, 4 lines of equal intensity. Obviously, this could be one doublet, this could be one doublet, or from the center of this could be one doublet, this could be another doublet, does not matter. We call this as doublets of doublet. What about this pattern? Very easily looking at the pattern, we already got one stick plot, we saw that. See, this and this will be one triplet, this and this will become another triplet, and this will be a doublet. So, what do you call that? Each line of the triplet, first it is going to be triplet, and each line of the triplet is split into a doublet like this, and that is how you are going to get triplet of doublets. What about this one? Larger separation is a doublet, and each line of the doublet is split into triplet like 1 to 1, 1 to 1 intensity. So, that is a triplet. Similarly, here also 1 to 1 intensity was there and it became doublet. Here 1 to 1 triplet, and each line of the triplet is going to be first doublet, and each line of the doublet is going to be a triplet. Okay, that is fine. What about this one? Again identical to this. This is also doublets of triplet. Okay. What about this pattern? It is a very interesting real spectrum of a molecule. Larger separation you can see here is a triplet 1 to 1, that is so first separation splitting pattern is a triplet, and each line of the triplet is split into a doublet, and separation from this line to this line, or from this line to this line, or this to this, or this to this gives rise to larger coupling, triplet coupling strength, whereas separation between these adjacent lines of this doublet gives you doublet strength. So, this pattern is called triplets of doublet. What about this pattern? This looks more complex, but I told you This is how we have to get the analysis done. It looks like a pentet sometimes or a sextet, but of course it is because of overlap of the coupling. Fortunately here there is not much of a overlap, very easily you can identify. If you carefully look at this pattern, you will see there is going to be one triplet here, larger triplet, and then each line of the triplet is split into another triplet like this. What do you call this? It is triplets of triplet, a realistic example. What about this one? It is doublets of doublet of a doublet. We saw that one example I gave you A, M, P, X, and I said each line is split into doublet, we got 8 lines, which is coupled to 3 other protons. Exactly here, one proton is coupled to 3 other protons. As a consequence, it is going to be doublets of doublet of doublet. Look at this one. This is a very interesting pattern. If you carefully see, initially it looks confusing, but if you carefully see this line, this line, this line and this line, one more here, it looks like a quartet. See, and each line of the quartet is split into a triplet. First it is a quartet and each line of the quartet is split into a triplet. So, it is called quartet of triplets. Larger separation is quartet and then each line of the quartet is split into triplets. What about this one? Of course, this is a doublet separation is larger and each line of the doublet is split into a triplet, it is called doublet of triplets. What about this one? Triplet of doublets, because this larger separation is a triplet and each line of the triplet is split into a doublet. This one very easily you can identify. First it is a large separation, is a doublet and each line of the doublet is split into a quartet. So, it is called doublet of a quartet or quartets. And this one again, this line central to this line is a doublet and then each line of this doublet is split into quartets like this. So, it is called doublets of quartets. What about this one? Very easily you can identify. It is similar to what we saw here, only thing is spread is larger, it is also triplet of doublets, larger separation is triplet. This is another thing. Here this is triplet of doublet, but here it is doublet of triplet, because this is a large separation and each line is split into a triplet. Larger strength here is a doublet, smaller coupling is a triplet, it is called doublet of triplets. This one, what about this one? If you carefully see, as you go now complexity will become better and more complex and you need to have some idea how to analyze. This is called triplets of a triplet. So, this one and center of this and this one for example is a triplet. First it is a triplet and each line of the triplet is split into another triplet like this. So, center of the line is a of this triplet remains unaltered, it remains same, frequency remains same, but then each line of this triplet central line remains same, is split further into triplet, 1 to 1 triplet. It is called triplets of a triplet. This is another interesting thing. If you carefully look at it, you can identify very easily it is one quartet, another quartet, and then center of this quartet to center of this quartet is a doublet. So, what we call this pattern? Doublets of a quartet. This is more complex. Now, we have to understand why we are going to get this type of pattern. If you carefully see, first of all you have to decipher, discerning of this multiplicity pattern is very important. If you have to look at this pattern first, I would say first center of this is a chemical shift, that is always I told you in the of the multiplicity. From the center first it is going to be a doublet and each line of the doublet is further split into two lines, doublet of doublet, and then each line of the doublet of doublet becomes triplet, one triplet, another triplet, another triplet. You see, all lines can be very clearly assigned, and this is what is called doublet of triplets. See, understanding the pattern is very important. You always start from the center of this multiplicity pattern. You should carefully think what could be the pattern. Based on that you can start arriving at it. Look at this one, even more complex. Of course, start from the center here, this is the chemical shift and it is a doublet and each line of the doublet is a triplet and each line of the triplet is again split into a doublet. So, it is called doublets of triplets of doublets. Here doublet of triplets, here is doublet of triplets of doublet. See, look at the pattern is completely different. If you carefully see here, pattern is completely different. See, everything is erased. Now look at the pattern, pattern is completely different here. This pattern and this pattern, see, completely different. So, doublet of triplet and doublet of doublets makes a lot of difference, especially in the appearance spectrum. Okay, now we will go to a realistic example of a molecule like this. Mercury 199 spectrum of this. We will discuss more about these things when we come to heteronuclear NMR spectrum analysis. Now, this is a particular molecule. There is this fluorine and this fluorine split this into a triplet because of equal strength. Similarly, this and this will split the mercury with equal strengths. All three fluorines of this vinyl group are inequivalent, but each of them is symmetric with respect to mercury. This is symmetric with respect to this, this is symmetric with respect to this, is symmetric with respect to this. As a consequence, what you are going to see is a spectrum very easy to understand. So, first this mercury is split into a triplet because of this. This will split this into a doublet, this will further split each line of the doublet into a doublet because of symmetry. Central line will overlap, as I have been telling you, it is a triplet. Now, these two fluorines will further split each line of the triplet into one triplet, another triplet and another triplet. What happened to other remaining fluorine? These two fluorine again are equivalent, it will split each line of the triplet into another triplet like this. So, it is triplet of triplets. This is a pattern you are going to see for this realistic molecule. Okay. Look at this molecule, this is 111 trifluoropropane. I am looking at the CH2 proton. There are 3 fluorines here, 3 protons here equivalent, CF3 group and CH3 group. Now, what is happening? I know the coupling, FH coupling I have written to you, this fluorine with this proton coupling, this proton to this proton coupling, strength is known. Then what is the pattern you are going to get? Because of these 3 equivalent fluorine, this is going to be a quartet. Again, each line of the quartet is split into another quartet because of protons. So, fluorine will split proton into a quartet, this CF3 split this CH2 into a quartet, and each line of the quartet is further split because of this and into another quartet. So, if this is one quartet and each line of this will be further split in another quartet like this. I see 4 different quartets, I put different colors to make you understand, and this is called quartets of quartets you are going to get. Okay. With all this thing, now we understood the multiplicity pattern and everything, but we should know what is the strength of the coupling. We have been discussing lot about multiplicity pattern, but if I measure the coupling strength, or if I do, even if I do not measure, I should have some idea what is the proton coupling strength. It could be 1 bond coupling, 2 bond coupling, 3 bond coupling. I told you coupling can extend up to 2 bonds, 3 bonds, and of course, as the number of bonds keeps increasing, consecutively this strength keeps coming down, does not matter, but each thing we should know the strength. Which is the 1 bond coupling among the protons? First thing you can think of is a hydrogen molecule, but how do you get the coupling here? It is a perfectly symmetric molecule, you are going to get a single peak. With single peak, how do you measure the coupling? At least it must be a doublet to measure the coupling, and it is a singlet. It is a different question, I will tell you later how do you measure coupling among the equivalent spins. But remember, coupling 1 bond coupling of proton is around 276 Hertz in the hydrogen molecule. Look at this type of molecule, we have CH3 and CH3. Again, you may ask a question, there is a symmetry and there may not be coupling. I told you these are all exceptions for 2ni+1 selection rule, but somehow we have some tricks we adapt and try to measure the coupling. Do not worry how we do and everything, do not come to a conclusion there is no coupling here. There exists coupling, but the couplings are not reflected in the spectrum, but we can somehow adapt some tricks to measure the coupling. Those things in the next class I will discuss. But in a molecule like this, that single bond, 3 bond coupling with this proton 1, 2 and 3 bond coupling is about 8 Hertz. And again, when there is a double bond, it is about 12 to 20 Hertz it can go. When there is a triple bond, it can be up the order of 9 Hertz in acetylene molecule. And also coupling depends upon angle between the bonds, depends upon what is it type of what is the angle in which these 2 protons are making. Look at this one, in a molecule like this, these 2 protons are trans to each other. Trans coupling is about 17 Hertz around approximately. It can be different, it can be 12 to 14, 15, 17, 18 Hertz also, does not matter. It is always, you should remember, trans coupling is always larger than the cis coupling. This is cis proton, 3J coupling, they are trans coupling, and this is geminal coupling. Geminal coupling is generally larger, M is very small, not large, it is very small. Geminal coupling is very small, then comes cis coupling, then comes trans coupling. Trans coupling is the largest of all in this type of molecules. Go to phenyl rings. If you go to the phenyl ring, as I told you, benzene gives a single peak. When I was discussing the magnetic equivalence, I told you each proton can have a orthocoupling, metacoupling and a paracoupling. If you consider this can have orthocoupling, metacoupling and paracoupling. Like each proton will have 3 couplings, and the strength of the coupling is about 78 hertz for ortho, meta 1 to 2 hertz and para from 0 to 1 hertz, less than 1 hertz. Okay. Then how did we measure this? All are chemically equivalent. Benzene I told you will give a single peak. If you take benzene NMR, proton NMR, it will give a single peak. Then how did you measure the J coupling? That is what I am going to tell later. And if you come to the 2 bond coupling, geminal couplings, I already told you, geminal couplings are very small, but in fact it depends again on HCH bond angle. In molecules like this, and also depending upon the substituents, hybridization at the around the carbon, all those things matters. What I am trying to give you is only the gist, a sort of a bird's eye view. You should not that all this type of molecule have the similar coupling. It can be different, but I am just trying to tell you this geminal coupling depends upon HCS bond angle and the hybridization of the carbon and type of substitution. For example, in this type of molecule, 2J coupling is 12.5 hertz and also with a negative sign, and in this type of molecule it is 4 hertz, and for this I already showed you in the previous example, geminal coupling is much smaller than cis coupling, and then even that is smaller than the trans coupling. So, this is what I said. Okay. And it depends also on the substitution at the position. For example, if you take CH4, it is going to be 12.4 hertz. Instead of one proton you knock it off and make it CH3Cl, coupling become 10.8. Knock off another proton, make it CH2Cl2, it becomes 7.5. It also depends upon the substituents. Not only HCS bond angle, depends upon the hybridization, depends upon the substituents, all those things matters. Extend further, in a molecule like this, 2 bond can be 6 hertz, here 5.5 hertz, and if there is a nitrogen here instead of C carbon, this 2 bond coupling can be very large. See, 2 bond geminal coupling in the ethylenic molecule I showed you about 2 to 3 hertz, but you see instead of C is double bond C, if it is N double bond C, then it is going to be even larger, 16 hertz. So, all those things you cannot remember and mug up everything because it is available in the books, but you should know all the coupling matters a lot. It depends upon varieties of varieties of substitution and varieties of parameters like HCS bond angle, etc. Take an example of a CH2CHX. Very easily you can write a structure like this, H and X. Now, depending upon the substitution of the X, 2 bond coupling can be different. If X is a lithium, 7.1 hertz, X is a proton, geminal coupling is 2.5, something else, let us say chlorine, OCH3, fluorine, it is different, couplings are different, that depends upon the substituents. In a molecule like this, geminal coupling can be 22 hertz. Remember, this coupling is 22 hertz, geminal coupling. But in other examples I showed you 2.5 hertz, in some examples I showed you it is about 6 hertz. So, it depends on the type of molecules. So, there is no general hard and fast rule, but it depends on the molecule. But by and large the guideline is such that trans coupling is larger than the cis coupling, this is larger than the geminal coupling in ethylenic type of molecules, but you have to carefully see about the substituents while arriving at this type of information. If you go to alkanes like this, it depends upon what is the bond angle it makes, what is the dihedral angle. See, for example, in this case you are going to get phi equal to 60, in this case phi is equal to 180, in this case dihedral angle is 60. And in such a situation, here 3 bond coupling is 2 hertz, here 3 bond coupling is 10 to 16 hertz. It depends upon how this in the C double bond C in N alkanes, what is the dihedral angle between these protons, these groups. So, on an average if you take 3 bond HH coupling is of the order of 7 hertz, because we have gauge and trans coupling to be taken, and then take the average of that, it is 7 hertz. It is an average conformation. If you get a 7 hertz coupling between these things, when you measure, then it 3 bond coupling is 7 hertz, means it is the average conformation. Cyclohexane, especially if you consider the chair conformation. Remember, when we analyze the spectrum of some of the cyclohexane, sugars, etc., we will discuss. Depending upon what is the conformation, chair or boat. If you consider chair conformation, axial coupling is always larger than axial equatorial coupling, and this is always larger than equatorial coupling. Remember, axial coupling is larger than axial equatorial, which is larger than equatorial coupling. For example, in a molecule like this, 1,2 coupling is larger, about 14 hertz, then 1,3, then 1,4 coupling is larger, see 2,3 coupling. This is simple, just general guideline. Of course, in this type of cyclohexane, when you have a chair conformation, by and large this order is maintained. By and large, axial coupling between two protons which are axial to each other, coupling is larger than axial and equatorial, which is larger than equatorial and equatorial protons. Go to cyclohexane alkane derivatives, coupling can be like this, axial equatorial, equatorial and axial. Again remember, axial is larger than axial equatorial, and then it comes to this. But in this case both appear to be similar, but of course as I told you, these are all the guidelines. In this case 3HA, HH is 4H, in 3G HH is 9 hertz. Usually 3 bond coupling is quite small, we say 1 bond coupling is larger than 2 bond and then 3 bond. Yes, but the coupling strength also depends upon whether the molecule is linear, which has a zigzag pattern, all those things matters. If you go to cyclopropane, if you consider this proton, depending upon whether the conformation is trans, what is the angle, transverse is, then in this case cis coupling is larger than trans. But remember, in the case of ethylenic group, I told you C double bond C with substitution, trans is larger than the cis. But in this case cyclopropane, cis is larger than the trans. These are all some of the things which you should know. And magnitude of the coupling in substituted aromatics. Consider a molecule like this, in an aromatic like this. As I told you already, orthocoupling is quite large, then metacoupling, then comes paracoupling. This is, in fact 1.5 is highest, we will get generally less than 1.5 hertz or something. This is 1 to 1.5 hertz metacoupling, but depends upon the substitution, where you are substituting, whether you are substituting the ortho position, meta position, para position, whether symmetrically substituted, disubstituted or monosubstituted, whether it is symmetrically disubstituted or asymmetrically disubstituted, everything matters. But always remember, orthocoupling is generally larger in phenyl groups than metacoupling, than paracoupling. That order is more or less maintained. And also it depends upon the bond strain, as the angle keeps on decreasing. Look at this is a 7 membered ring, then 6 membered ring and 5 membered and 4 membered ring. Here the coupling is quite large, is of the order of 5.7 hertz. Here it is 3.1 and 1.1. You see, as you decrease the bond angle between the HCS bond angle, the coupling strength comes down. Coupling constant decreases with the bond order. They look at this one, this is 11.6, in this case 7.6, in this case 8.6. And heterocycles, if you consider, generally they will have a smaller coupling constant compared to hydrocarbon. Heterocycles have a smaller coupling. Look at this one, this is a heterocycle. Here orthocoupling is 6.9, in this case orthocoupling is 4 to 6 hertz. Otherwise in benzene I said it is about 78 hertz, sometimes 8.5, 9 hertz like that. Look at this, it is 1.9, 5 point here. If you consider furan, this coupling is smaller, where this is even smaller, but though it is orthocoupling. So like this, coupling depends upon varieties of information. I will give you something about what is called a Karplus curve. We can use a 3 bond coupling to get some information about the dihedral angle. This is a famous equation. Why it happens? Because the magnitude of the J coupling depends upon the bond angle, overlap of the orbitals. So that means J value depends upon the dihedral angle. That is the conclusion. So JHH is maximum when 2 CH bonds in a molecule like this, HCCH if you consider unit, when 2 CH bonds are parallel. Parallel means it is 0 degree or 180 degree dihedral angle, then J coupling is maximum. J coupling is minimum in this type of molecules, HCCH, if this bond angle, dihedral angle is 90 degree, where that is important, you should remember. So for example, if it is eclipsed, if it is 90 degree, if it is trans or anti, you can find out. If it is eclipse 0 degree, coupling is this much. If it is 90 degree orientation, 3J coupling is 2 hertz, and if it is anti 180 degree, it is 13 hertz. So, I said 3J coupling is very important, that throws light on the conformation of these molecules, very important. And how do we get this dihedral angle? This is given by a famous equation called Karplus equation. Remember, A into A plus B cos squared phi plus C cos phi is a famous Karplus equation. It is a quadratic equation in cosine of phi. You can have infinite solution for different phi values. If a phi value is fixed, it has 4 solutions, because quadratic equation has 2 solutions, and cos phi and cos minus phi are same. So, it will have 4 solutions. So, that is one thing. If the phi value can vary, you can have infinite solution. This is a famous Karplus equation, and A, B and C are the constants which are arrived at empirically to fit the curve. Okay. The curve is also different, which I did not show, that it is going to be an enormous discussion, but basically you get the idea. 3 bond cis coupling or this trans coupling, whatever we get, 3 bond coupling 3JHH, we can use to get the dihedral angle, and this is the idea. In the olefinic systems, trans coupling is always larger than cis. In the 1,2 disubstituted ethane which we saw, gas is larger than, less than trans, and using Karplus equation we can obtain the dihedral angle, and or we can estimate it by measured 3JHH. If you take saturated hydrocarbon, if the J coupling is less than 2 hertz, I showed you here, J coupling is less than 2 hertz here approximately, that means dihedral angle is 90 degree, that is the idea. So, here also you can get the information. If J coupling is of the order of 2 hertz, then probably they are the dihedral angle is 90 degree to each, 90 degree between them. Okay. And in acyclic system, if you consider, 3J coupling is usually associated with anti relationship, small coupling correspond to gauge relationship, and vicinal coupling of order 7 hertz is nothing but time average conformation averaging. That is a guideline for you to understand. So, vicinal coupling, simply you understand, axial coupling gives you 180 degree is 11.8 hertz, axial equatorial is 3.9, equatorial 60 degrees smaller. So, in the chain conformation of cyclohexane, the coupling between 2 axial protons is always larger than equatorial. I have been telling you, please remember, if you have a chain conformation in a cyclohexane, axial coupling is larger than axial equatorial, and then that is larger than equatorial. So, equatorial coupling is smaller always compared to axial coupling, and this is the idea, you can use it. We will analyze one or two of the sugar spectrum of the D glucose, we will understand. Go to sugars, 3JHH coupling is used to distinguish alpha glucose and beta D glucose. Take D glucose, we have alpha glucose and beta glucose, the structures are like this. For example, in the alpha glucose, axial equatorial coupling is 3 hertz, but in the beta glucose the structure is different. As a consequence, axial cup orientation is there. In beta has axial orientation between these 2 protons. As a consequence, coupling is larger. In this case, it is axial equatorial orientation, coupling is smaller. So, if you have a sugar molecule, measure this coupling, then you know whether the coupling is smaller or larger. Based on that, you can say whether it is alpha glucose or beta glucose, very easily you can get it. So, cis trans isomers in the olefins, 3JHH trans is always larger here than cis. This is basically an idea you should know to measure the get the conformation. Long range couplings, generally after 3 bonds coupling will drastically come down. 4 bonds most of the time it is 0, you will not see. But there are classic examples like this. This 4 bond coupling can be of the order of 9 hertz, 5 bond coupling can be of the order of 3 hertz is there. And depending upon this, there is a linear chain like this or a zigzag fashion like this type of molecules, you can have 5 bond coupling, 4 bond coupling, etc. And in the classic example, 5 bond coupling is of the order of 3 hertz, and I will go to a bigger molecules, we can get 5 bond coupling of even 5 hertz. And in this type of molecules, linear chain, you can get 6 bond coupling. 5 bond coupling is very regularly you can see 3 to 6 hertz. This is rare, I tell you, it is not easy, because after 2 or 3 bonds drastically the coupling strength comes down. But these are all classic examples where you can get the coupling even up to 5 bonds, 6 bonds also. In an example like this, if you look at the coupling between this proton and this proton separated by 9 bonds, you can see of the order of 0.4 hertz. So, in principle we say as the number of consecutive bonds increases, the strength of interaction comes down. It is true, but there are examples in a linear molecule like this and a molecule which has a zigzag pattern, significant coupling strengths, very large coupling strengths of 4 bond, 5 bond, 6 bond, even in sometimes 9 bond have been observed. This is what I wanted to tell you. And last I want to tell you, remember when we were discussing the chemical shift, I said chemical shift is dependent linearly on the magnetic field. As the magnetic field increases, the chemical shift dispersion changes. I showed several examples, 200 megahertz, 400 megahertz, 600 megahertz. In the ppm scale it remains same, but in the frequency scale I showed you how the spreading becomes better and better. The same thing. Now what will happen if to the J coupling when you change the magnetic field? You will understand this one. Let us take an example of a proton spectrum at 200 megahertz. I have a triplet and a quartet, and 0 ppm is somewhere there tetramethylsilane. This is the chemical shift of one proton, this is CH3, this is CH2. CH2 is a quartet because of CH3, CH3 is a triplet because of CH2, and this is at 1 ppm, this is at 3 ppm. And what do you get? This is in frequency, this is 200 hertz and 600 hertz, that we know. And if this adjacent lane separation gives you coupling constant, fine. Now I am going to double the magnetic field. I go to higher frequency spectrometer, 400 megahertz, 1 ppm remains same, 1 ppm, 400 hertz, and 3 ppm remains ppm scale, but in frequency it is 1200 hertz. Okay, there is a lot of dispersion. I told you in the chemical shift there is a linear, it changes linearly with the magnetic field, we have dispersion. What about this J coupling? The adjacent line separation, if you measure J coupling, 8 hertz here, 8 hertz here, here also 8 hertz. What does it mean? It means J coupling, whether you go from 200 to 400 megahertz or go to 800 megahertz, does not matter. J coupling is always invariant with the magnetic field. J coupling does not change with the magnetic field, it remains same. Only chemical shifts varies linearly with the magnetic field. Okay, so with this more or less I have covered lot about this scalar coupling information I gave you. Today in fact we discussed a lot about varieties of multiplicity patterns and took number of examples, realistic examples, and see, looking at the complex multiplicity pattern, how do you put a nomenclature for each of these multiplicity? What is the doublet, triplet, doublet of triplet, triplet of quartet, all possible examples we took. And afterwards I showed the strength of the J coupling. One bond coupling is among the, in a hydrogen molecule is quite large, 276 hertz. As you go to other different type of molecules like ethylenic molecules, I showed trans coupling can go from 12 to 14 or 18 hertz, whereas cis is larger, 6 to 10 hertz, geminal is very small to 1 to 2 hertz or 3 hertz, depending upon the substitution and depending upon what is the type of this thing, whether it is CC bond or CN bond, again it changes. And also in the, if I take the example of phenyl group, I showed you ortho coupling is about 7 to 9 hertz, meta is 1 to 3 hertz, whereas para coupling is less than 1 to 1.5 hertz. But all these are chemically equivalent, but still we got a single line, but there is a way we can get the J couplings. That information how we get it is different, we will work it out. So number of such example I took, and I said 3 bond coupling can be utilized 3JHH and fit it in the Corpus equation, the quadratic equation of cosine of phi, you can get the dihedral angle. The coupling depends on 3 bond coupling can be used to obtain the conformation, obtain the dihedral angle in many such molecules, cyclohexanes, the chair conformation of cyclohexanes. We can use the 3 bond coupling to distinguish between alpha glucose and beta glucose, that is what I said. And further finally I also showed you J coupling, if you measure in a given molecule at any particular frequency, double the frequency, go to any other spectrometer frequency, it remains same. So J coupling does not depend upon the magnetic field, it is invariant with the magnetic field. This is a very important parameter, you should remember. Chemical shift changes linearly with the magnetic field, whereas J coupling is invariant with the magnetic field, it remains same. So this is what I wanted to tell you. With this I have covered extensively for scalar coupling, etc. Next class we will start interpreting the NMR spectrum. How do you analyze the spectrum, right from spin system nomenclature, Popper nomenclature, and then realistic example of the analysis we will start. So I am going to stop here. Thank you very much.